Hi everyone. So this is going to be a very short lecture. I'm just going to introduce a few simple concepts and definitions, but that's going to be fairly short. So now I'm starting to look at the current at the microscopic level. What is really happening? Okay, so if you look at any material, anything, any gas, solid or liquid, you have protons, neutrons, and electrons. So you have nuclei in which protons and neutrons are bound, and then we have electrons. Now we're going to distinguish between what are called bound electrons, which are electrons that are uh, stuck in orbit around the nuclei. So those are in orbitals, and they cannot escape from the atom. They're stuck there. Okay, and then we have free electrons. If you look at the farther shells, the farther orbitals, some of the electrons can escape and start to move freely inside the material. Those we call free electrons. Um, they are very important for us this semester because what is creating a current in a wire, for example, are the free electrons. The reason for that is that if you apply an electric force inside the material, the nuclei, they feel electric force, but because they're so heavy, because they contain protons and neutrons, they're so heavy compared to electrons, the nuclei don't move much. You push on them, but they're very heavy, so they have very small acceleration. The bound electrons have small mass, but because they're stuck on because of the attractive force from the nuclei, they have to follow the nucleus. So they cannot escape, they stay stuck. The free electrons, those are free, and because they have a very small mass, you push on them a little bit and they will move easily. So those are the ones that are creating the current. Okay, so the picture we have of some material, let's say wire, in which you have some current, is that you have, let's say, nuclei. Those are the nuclei. Around the nuclei, you have the bound electrons. Now here I drew only one bound electron for each nucleus, but of course, if you have a wire made of copper, for example, you have many bound electrons. Okay, so you can have 5, 10, 15 bound electrons per nucleus, depending on the material you're looking at. So I just drew one of them. Now, then those are stuck with the nuclei, so everything here is not moving very much. But you have free electrons. Those are free to move. So if you apply a tiny force, even a small force, they will move easily. And here I drew them like this. So here I assume that there's an electric force on the electrons, and here in green you have free electrons. So let's say there's an electric force to the right, so the free electrons all move in that direction. But the nuclei and the bound electrons do not move, so they don't participate to the current. Now keep in mind that here I'm drawing the electrons. You have free electrons moving to the right, but when we talk about current and definition of current, we think in terms of those fictitious positive charges. So for every free electron here that has a negative charge, moving to the right, I imagine I invent a fictitious positive charge with the same charge as electron but positive, moving in the opposite direction. So in this picture here, you have your free electrons moving to the right, but the current is moving to the left because the current is in the direction of the motion of those fictitious charges. Okay, so that's the picture of a current in a wire, for example. Things are going to get a bit more. It's actually a bit more complex than this, but we'll talk about that next lecture. But for now, that's good enough. Okay, let me introduce a few symbols. Well, most of that you already know. So you have Avogadro's number, which is defined to be the number of atoms in a mole. Okay, given by that number. Um, then in our equation, we also talk about the density of a material. That's just mass per volume. Okay, so we use the Greek letter rho for the mass per volume. So rho would be kilogram per meter cube. Then there's a special mass called the molar mass of a certain material. So each different, if you look at copper, carbon, neon, any material has a different molar mass. The textbook uses capital M for the molar mass in some problems, but it's a bit confusing because in the density here, this mass can be the mass of anything. Okay, this is the mass of any object. The molar mass is by definition the mass of 1 mole of that material. So it's a special mass. So here in my presentation, I'm going to keep it call it m mole to remind you that this is just a mass for 1 mole. Now this number, this value here is different for different materials. How do you find that? So let me get out of the presentation for a second, and I'll go to WebAssign and show you how to find the molar mass when you're in WebAssign. So let me switch to WebAssign. Okay, let me go back to, let me make a little change. Okay, let me just make a few comments about WebAssign, even though you know how to use that. If when you go in the ebook, you have the table of contents here. You click here, you have the entire book here. But you'll have to go click on assigned readings. This is the section that I have edited. So you have my just the chapters of electricity and magnetism here. And notice another thing is that the first chapter on electricity is chapter 23, but I've changed the order. We're not following the order of the book. So I've put chapter 27 on current and resistance as the first chapter. Okay, and in that chapter, if you look at that chapter here, I've made some, I've put some comments, I've deleted some lines, I've added some extra comments and so on. So I'll give you some reading to do later on, but I've started to work on that chapter and make some changes. Notice that we're not going to cover everything in that chapter, and I have, for example, deleted some sections on things that we're not going to cover, but you'll have to read that a bit later. Okay, now let's go back to the molar mass. If you go in the assigned readings, but you go down in appendices, you go appendix C, you have the periodic table of elements, and you see here you have the left side of the table. Let's click here to go to the right side. Okay, and then for each atom you have the number of protons. So carbon has 6 protons and so on. And then you have this blue number is important. This is the molar mass. So what is that? Let's say you have carbon. This blue number is the mass in grams, not in kilograms, but in grams. The mass in grams of 1 mole of that element. So carbon has a mass of 12.011 gram per mole. I'm going to use this number in a minute. For copper, the molar mass of copper is 63.546 gram per mole. So that's the mass in gram of 1 mole of copper. Okay, so I'm going to use that in a second. Let's go back to the presentation. Okay, so that's how you get the molar mass by going to the periodic table. Now introduce a new thing called the lowercase n is the density of free electrons. So that's the number of free electrons per meter cube that a certain material has. Okay, so how many free electrons in each meter cube of material you have. This number can be calculated in the following way. For a given material, let's say copper, it turns out that if you take an atom of copper, each atom contributes 1 free electron. So there are several electrons in copper, but there's only one that becomes free for each atom. You have some other materials that each atom might give 2 free electrons or 3 free electrons, but for example, in the case of copper, you have only 1 free electron per atom. So for a given element, you multiply the number of free electrons per atom by the number of atoms per meter cube, and that gives you, of course, the density of free electrons, how many free electrons per meter cube. Okay, we'll do an example in a minute, but just one comment here. Um, so this is the number of free electrons is different for different elements, and this is what makes the difference between a good conductor and um, uh, something which is non-conducting. For example, copper, aluminum, and so on, they are good conductors. That's because the atoms provide free electrons to participate to the current. There's some materials that are not good conductors, and the reason for that is that they don't give free electrons. So then there's no free electrons around, or very few free electrons around to participate to the current. So they're not good conductors. Okay. Okay. So let's look at. Okay. Now these are the basic definitions here that we just seen. From these, you can calculate a lot of different things, but if you understand what each of those things means, then you can get other relationship. For example, um, let's say you want the volume occupied by 1 mole of a certain material, let's say copper. Given all the information given here, how do you find the volume occupied by 1 mole? Well, it's pretty clear. You want the volume, and the volume from this equation here, the volume is a mass divided by a density, the density. So if you want the volume occupied by 1 mole, you take the mass of 1 mole and you divide by the density. That gives you the volume occupied by 1 mole, by definition. Okay, so this is an implication of, it's a special case of this equation here when you just use a mass of 1 mole. Therefore, you get the volume of 1 mole. Something else you can calculate is, okay, what's the number of atoms per meter cube of a certain material? Let's say you take 1 meter cube of copper or gold or whatever you want. How many atoms are contained there? Well, it's simple. You want the number of atoms per meter cube. So you know that if you take 1 mole, it contains Avogadro's number of atoms. So you just have to take the Avogadro's number divided by the volume of 1 mole. That will give you how many atoms there are per meter cube, because you know that Avogadro's number of atoms occupy the volume of 1 mole. So divide that number here by the volume of 1 mole, you get number of atoms per meter cube. Notice, if you look at this equation here, we already calculated the volume occupied by 1 mole. It's mass of is the molar mass divided by the density. So if I plug this quantity here into this equation here, I replace the volume of 1 mole. I take Na divided by this, I get Na rho over the molar mass. So the number of atoms per meter cube is can be calculated by this equation here. That's a shortcut, but that's where it comes from. Okay, so now we can talk about just a quick example, copper. Okay, so if you're given let's say you're working with a wire made of copper, you have to be given some information. The molar mass, I don't have to tell you. If I give you the periodic table, or you have your textbook, go to your textbook, in the appendix on the periodic table, you find the molar mass. That you know. We saw it a minute ago, it was 63.5 gram per mole. Okay, that's the molar mass, so you know that. You have to be told the following information. This you could not find by yourself. You have to be told, provided the information. I'm telling you, in copper, there's 1 free electron produced per atom. That's something you have to be given. Another information you need is the density of copper. You can look it up on the internet, of course, but let's say you're given that value. Density of copper is 8.92 gram per centimeter cube. Okay, now given this and those two values and the molar mass that you have from the book, you can do calculations. Now, just a warning, there is a common mistake in those calculations people make, is that you see you have you have here density per centimeter cube. Often you'll have to convert centimeter cube to meter cube, and people often make the following mistake. They'll say, okay, 1 centimeter is 0.01 meter. Therefore, they'll say 1 centimeter cube is 0.01 meter cube. This is wrong. Okay, this is what people often say, because they're used to think of 1 centimeter as being 0.01 meter, but it's not true that 1 centimeter cube is 0.01 meter cube. The correct way of thinking is that 1 centimeter cube, if you want, when you write that, 1 centimeter cube, this is the same as 1 centimeter cube. So it's the whole 1 centimeter that is cube. Now 1 centimeter cube is 0.01 meter, all that cube. So you have to cube the 0.01. So 0.01 is 10 minus 2. You cube that, you get 10 minus 6. So the end result is that, as you see here, 1 centimeter cube is actually 1 centimeter cube is a millionth of a meter cube. Okay. Now we can do examples. For example, what's the volume occupied by 1 mole of copper? And let's say you want the volume in meter cube. 1 mole of copper, from the information you were just given, and you might need the molar mass. Okay, I won't tell you what you need for this calculation, but if you need the molar mass of copper, you look it up in the textbook. We saw it a minute ago. So calculate. This is really a question. You should try it. I'll give the answer in a minute, but you should pause now and be able to do the calculation. What's the volume occupied by 1 mole of copper? Give the value in meter cube. What's the number of atoms of copper per meter cube? So in 1 meter cube, how many atoms of copper are there if you have 1 meter cube of copper? And what is the density N of free electrons in copper? So how many free electrons per meter cube, that's what N is, are there in copper? Okay? You have all the information. You should stop the recording here and be able to do the calculation. I'll give the answers now, but you know everything now to calculate, to answer those 3 questions. Okay, ready? Here are the answers, and you can check yourself. So the volume occupied by 1 mole of copper is 7.12 times 10 minus 6 meter cube. The number of atoms of copper per meter cube is 8.45 times 10 minus 20, 8.45 times 10 to the 28. Sorry, my system is responding very slowly. Okay. Okay, so the volume occupied by copper is 7.12 times 10 minus 6 meter cube. There are 8.45 times 10 to the 28 atoms of copper per meter cube. And now, because I told you that each atom of copper gives 1 free electron, then the number of free electrons per meter cube is also 8.45 times 10 to the 28. So in the case of copper, the number of atoms per meter cube is the same as the number of free electrons per meter cube, because each atom gives 1 free electron. Okay, that will be all for this lecture. Thank you.